Hi, I'm Eusebio Rufián Zilberman from Long Island, New York, and this is a presentation for the course Introduction to Music Production. Today's presentation is about the reverb effect, and in particular we will compare convolution and algorithmic reverbs. What is convolution reverb? Convolution is a mathematical operation on two functions. It is the integral of the product of two waveforms after one has reversed and shifted. If you're not that mathematically oriented, you can think of it as a special way to multiply two functions. In digital signal processing, we have some interesting functions, impulse, step, and sinusoidal responses that let us extract audio properties useful for convoluting. If we have a linear time-invariant system, its impulse response is very useful because convoluting a signal with it will reproduce the changes that the LTA system would have applied to the original signal. Something like a room can be modeled as an LTI. It is linear because it doesn't have saturation and distortion. It doesn't change with time, so it is time invariant. The impulse response of a room can be used with convolution to accurately modify any signal in the same way that the room itself would have modified it. What are the advantages of a convolution reverb? Well, it is a recording and it can provide the most realistic effect. What are the disadvantages? Configuration of the effect can be comparatively limited. It's less flexible. As we can see in the screenshot, we can choose the impulse that will be applied. Many of the other options that we can configure are really dynamic and filter effects, like envelope, panning, and equalization. Good convolution reverb will have an algorithm that is computationally fast, and it will also include a large library of impulses. When recording impulse responses for a library, we're not limited to recording rooms. We can also record specific devices, like microphones, or even a spring or a metal plate. The limitation, though, for these devices is that if they saturate, a device like a microphone is not exactly linear, but we can use convolution for simulating the linear part of its response. What is algorithmic reverb? Algorithmic reverb is a calculation from a mathematical model of the reverb operation itself. Depending on the sophistication of the model, it can have a large amount of configurable parameters. Let's see a simple example first. The advantage is that we have parameters that are easier to understand, like the type of reverb, which gives us the algorithm that will be used. We have the room size that will give us the early reflection properties of the reverberation. We have the liveliness, which will apply to the feedback property of the reverberation. And we have dry-wet mixing. The disadvantage of algorithmic reverb is that the results are less realistic compared to convolution. And in this particular case that is simpler, the simplification comes at the price of flexibility. Let's look at a more sophisticated example. Here we can choose the reverberation, which is the algorithm that will be used, separate dry-wet mixing, the early out, which will give us the feedback property of the delay, the early reflection style, which will control the delay time, which will give us the room size. We can control the decay time, the pre-delay, and we also have equalization. All these parameters are fully automatable, which gives us an incredible amount of flexibility. The disadvantage is that the results are less realistic when compared to convolution. We're done with the theory. Let's listen to an example now. This is a sound before applying reverb. This is the recording after applying the convolution reverb. This is a sound after applying an algorithmic reverb. In summary, convolution reverb calculates reverberation based on a recording. It provides the most realistic effect. Algorithmic reverb calculates reverberation based on a mathematical model, and it can provide the most flexible effect. That's all. Thank you very much for listening.